Good afternoon, class. Today what we're going to be looking at is the start of chapter 12, which basically means we're going to look at solids. And solids are shapes that are essentially three-dimensional. So they can be like cylinders, they can be prisms. I'm not exactly sure what I call this one geometrically, but let's call it an egg. Spheres, hemispheres, cubes, pyramids. They're all these shapes that are solid. They're all solids, which basically means that they form a three-dimensional volume, essentially. And they're made up of faces. So we're not just looking at two-dimensional stuff anymore, it's three-dimensional. And with that, we have new vocabulary. The first new word is polyhedron. Now, if we think back to polygon, polygon meant poly, multiple, gon kind of meant sided. So, multiple sided. So, polyhedron is probably multiple faced. And what we mean by polyhedron is that each face is a polygon. So, for instance, this is a polyhedron because this is a square, this is a square, this is a square, 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 and square. All of its sides are polygons. This is a polyhedron because square, trapezoid, 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 square. All of those are polygons, so this is a polyhedron. But when I look at something like this or this, these aren't polyhedron because its surface, its face, isn't a polygon. Even this one, yeah, it's a shape we know, it's a circle, but that's not a polygon. So, polyhedron just means it has multiple faces that are polygons. Anytime I look at two faces intersecting, like this one here and this face here, this crease is what I call the edge. So if I ever say edge from here on out, I'm talking about this here. If I say face, I'm talking about this. If I say side, we better be looking at a two-dimensional shape and looking at the edge, or this part here. So, edge between two faces. Faces is the entire surface on one side. Vertex is where three or more faces meet. So this corner right here, vertex, corner, vertex, corner, vertex. So wherever three edges meet, or wherever three faces meet, we will get a vertex. By the way, if I had multiple polyhedra in my hands, the plural is polyhedra or polyhedrons. Either is acceptable. Alright, there's another thing that we are going to look at. We should be able to classify them pretty quickly at this point, at least a few of them. If it looks like this, this, or this, where you have two bases, we call it a prism. Two bases connected by quadrilaterals. Prism. Two bases connected by quadrilaterals. Prism. Two bases connected by quadrilaterals. Prism. The only thing that has to be for sure is that these bases have to be parallel, but the quadrilaterals doesn't mean it's going to be straight up and down. Pyramids. One base, and each other side is a triangle. That means I could have a pyramid that looks like this, which there's a distinct difference. Its base is a triangle for one of them, where the other is a square. So, you should be able to tell me some of the things on the side of the shape, like for instance the edge, the vertex, the face, by identifying. You should be able to look at this and say prism, pyramid. Maybe you've got cylinder, but we'll get to that one later. And maybe you already know cone. Looks like an ice cream cone. And there we go. So, cone, cylinder are the two that I haven't gone over yet. Alright. Now, here's some pictures. Drawing these aren't necessarily going to be the easiest thing. And when they're drawn, we have to know a few things. Anytime I see a solid line, I can physically see it. So right now, if you were drawing this shape here, you would draw this line, this line, this line, this line, this line, and these two up here in my picture. So if I was going to try and do that, I would draw this. And that's what you could see if I was holding it something like this. Okay, maybe it's a little bit more like this, but you get the idea. That's what you can actually see. Now the lines in the back that you can't see, they're still there, but we dot them to let us know that it's in the back. So what you should see is that this corner is in the back. These other corners are in the front where you can actually see them. Now, just to note, if I want to do dotted lines, I would see something like this. So, without dotted lines, let's look at this. I have a question for you. Is 1 or 2 the front surface of my cube here? Well, if I'm thinking 1 is my front surface, I'm looking at my cube like this. But if I think 2 is my front surface, I'm looking at my cube like this. And because there's no dotted lines, it's not clear. So please include dotted lines so we can visually see. Here, you should see this surface as the front surface, and it should be almost straightforward, quick. Here, you can actually play with your eyes a little bit here in your mind, and you can switch back and forth between 2 being the front surface and 1 being the front surface. So, please include the dotted lines. It locks it into one shape. So when you look at these 5 pictures, yeah, it identifies it, but anytime there's a dotted line, you can't see it. Okay, yeah, we put in the picture so you can see the whole shape, but it's not actually visible from our perspective. All right, last but not least, the last type of classifications that we might have, besides these, polyhedra, not polyhedra, prism, pyramid, cylinder, cone, sphere, is this. There's 5 what we call Platonic solids, named after Plato. And what's so neat about these solids is they can be regular. Regular. That doesn't mean normal. It doesn't mean same or anything like that. It means that everything is congruent. The surface will be congruent to the surface. A face will be congruent to a face. An edge will be congruent to an edge. Every length and area in it will be congruent to another length and area in it. So, for instance, when I look at the cube here, this is a Platonic solid because all 6 sides are squares and each edge will be the same length. Platonic solid. Now, there's actually one using regular triangles called the regular tetrahedron. Tetra, 4, hedron, faced. Alright, so regular tetrahedron just means it has 4 congruent triangles that are regular for each of its faces. Now this isn't a true regular tetrahedron. It is a tetrahedron, but it's not a regular one. A regular octahedron. All the sides are triangles. It's basically 4 on top, like a pyramid, and 4 on the bottom. The dodecahedron I actually have. Alright, I actually do have a regular dodecahedron. Dodeca 12 hedron faced. And it's actually made of pentagons, 5-sided shapes. There's 12 of them in here. And they're all the same size pentagons. And we call it a regular dodecahedron because each surface is a regular pentagon and each edge will have the same length. And I don't have the regular icosahedron. Icosahedron. It's a 20-faced one. The last one there is 20-faced. The prefix means 20. Hedron means faced. Now, these are the only 5 there are. There isn't another one. I can't make another one using a regular triangle, square, a regular pentagon, or even a regular hexagon. In fact, when I do a regular hexagon, it fails. It does not work. It only works for these 3 shapes, triangle, square, and pentagon, and these are the only regular polyhedrons, which we call Platonic solids. Alright, so we've identified them. We should now be able to name them. A fair question at this point would be, tell whether the solid is a polyhedron. If it is, name the polyhedron and find the number of faces, vertices, and edges. So if I look at this first shape here, I see one rectangle and then each of the other sides are triangles. Wait. If it's one face that's kind of this, and then everything else is a triangle that meets at one point, it's a pyramid. Okay, so I'm going to call it polyhedron pyramid. And then after that, the number of faces, well, I actually have a solid model here to use. So 1, 2, 3, 4, 5. I count 5, 4 around the edge, and then 1 at the bottom. 5 faces. How many corners or vertices? 1, 2, 3, 4, 5. So I have 5 faces, 5 corners, and then I'll have 1, 2, 3, 4, 5, 6, 7, 8 edges. The second one, I see two faces that look to end up being parallel and connected by a quadrilateral or a surface. However, this front face here, this one right at the front here, that's not a polygon. So I know it's not a polyhedron. So number 2, not a polyhedron. Alright, and number 3, if I look, triangle base connected to a triangle base by quadrilaterals. So wait, triangle base connected to triangle base connected by quadrilaterals. It looks like this. So I'd call it a triangular prism. As a triangular prism. Now, how many faces does it have? 1 front and back, and then 3 around the edge. So I count 5 faces. Now, the number of edges: 1, 2, 3, 4, 5, 6, 7, 8, 9. I count 9. And the number of vertices: 1, 2, 3, 4, 5, 6. I count 6. And there we go. So the first and third one end up being a polyhedron. The first one was a square pyramid. The last one was a triangular prism. The number of faces were the same for both of them at 5. The edges for the first was 8. Edges for the third one was 9. Vertices for the first one was 5. Vertices for the last one was 6. And there we go. That's example 1. Now, there's something kind of neat. Euler, a famous mathematician, discovered something. It's that if I look at a polyhedron and I count up the number of faces and the number of vertices, that should equal the number of edges plus 2. Well, we just did a problem. Let's see if it's true. So if I add the number of faces to the number of vertices, that should equal the number of edges plus 2. So the number of faces in this one was 5. The number of vertices was 5. The number of edges was 8. So 5 plus 5 is 10. 8 plus 2 is... it worked. So let's look at this one. Well, that means I do 5 plus 6. That should equal 9 plus 2. 11 equals a... Wow. Euler's theorem does work. And it's not coincidental. In fact, any solid will have this happen. Any shape I look at, doesn't matter what it is, as long as it's a polyhedron, the number of edges plus 2 equals the number of faces plus the number of vertices. Whoa. So, with Euler's theorem, let's just do this quick. Find the number of faces, vertices, and edges on these polyhedron. I forgot to add a little thing at the end of that, and that's verify using Euler's theorem. Alright, so for the first one, I'm doing with a cube. So, count the number of faces. 1, 2, 3, 4, 5, 6. I count 4 along the edge, and then 1 for top and bottom. So 6 faces. Number of edges: 1, 2, 3, 4 for the front. 1, 2, 3, 4 for these sides, and then 1, 2, 3, 4 for the back. So that's a total of 12. The number of corners: 1, 2, 3, 4 for the front one. 1, 2, 3, 4 for the back one. So I count 8. Verify real quick. 6 plus 8, does that equal 12 plus 2? Does 14 equal 14? Awesome. The next one, pyramid. It's one like this. So again, count the number of faces, count the number of vertices, and count the number of edges. If done correctly, this is what you should have got. And when you verify, you do 5 plus 5, does that equal 8 plus 2? And again, 10 does equal 10. I realize we just did this one, so that's why I went a little bit quicker. So yeah, there we go. Alright, now, even though we're good at looking at shapes, what if I just told you something about a shape and I wanted to find out the last piece of information? Well, if you know the number of faces, vertices, edges, it's basically find the last one, use Euler's theorem. So it says find the number of edges, vertices, or faces for each polyhedron. And there's 3 of them. Alright, these are the 3. And what I want you to do is watch the first one and then try the next 2 on your own. So, the number of faces, I don't know, so capital F. But the number of vertices I know is 5, and the number of edges I know is 7. So I plug that into my equation. Solve for F. So F plus 5 equals 9, so F is 4. This one has 4 faces. Quickly try the other 2. If done correctly, you should have got 12 for the number of edges for number 2 and 28 for the number of edges for number 3. And there we go. That's using Euler's theorem. So at this point, we should be able to classify the shapes, identify what they are, and be able to count the number of faces, vertices, and edges, and relate them through Euler's theorem. Let's add in one extra dimension to this. What if I don't give you a picture and I don't tell you the number of faces, vertices, or edges, but I say, hey, find the number of faces, vertices, and edges of a regular octahedron. Check your answer using Euler's theorem. Let's quickly, first of all, have you try to draw an octahedron. Alright, I realize my perspective drawing might not be the best. However, I drew an octahedron. It has 1, 2, 3, 4 surfaces on the top, and 1, 2, 3, 4 surfaces on the bottom that are all regular triangles. Now, yeah, I didn't draw it necessarily regular, but these are a little bit hard to catch by hand. So, the number of faces, I just told you, it's octahedron. It should be 8. Now, the number of vertices, I count 1, 2, 3, 4, 5, 6 corners. And last but not least, the edges for Euler's theorem. Well, I count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I count 12. So let's check. 8 plus 6. Does that equal 12 plus 2? Does 14 equal 14? It does. And there we go. I've counted the number of faces, vertices, and edges of a regular octahedron, and I checked it. Yes! There's one last thing we need to go over. So I need to be able to identify and use Euler's theorem as appropriate. But there's one last thing. There's something that we call a cross-section. And what we can think about this is it's a section of our shape. And when I say cross-section, we're cutting across it. Alright? So for instance, what if I had this shape, and then I went cut right down the middle this way? Well, I would get a shape on the bottom that would look something like this. So what I've done is I've cut across here with a plane. Now, the cross section that I would have made would have been this right here. So the cross section is the shape formed by cutting the shape. Let's clarify a little bit. It's the two-dimensional shape formed by cutting a solid with a plane. So if I'm going to cut this with a plane right here across, I would end up getting a square. Well, what if I would cut this shape down the middle this way? Well, if I cut it straight down this way, then I would get a hexagon as my cross section. Well, what would happen if I went here and I cut it right there? So if I cut it along the line of the marker, I would get a quadrilateral as my cross section. Because when I would cut this down the middle, I would get this edge, this edge, this edge, and this edge. Four-sided quadrilateral. What if I would go here for this shape and cut off a corner? So I'm cutting this corner off right here. Well, I'd get this side, and this side. Three-sided, it's a triangle. If I look in this picture here, how they represent it with a picture is that this tan-ish or off-white plane cut into this triangular prism. And as it cut across, it cut this shape out right there. So this shape that it cut out is what I call the cross section. It also ends up being a light purple, and you can see that it's a smaller triangle. So the cross section in this case, a triangle. So now for each of these, the off-white color is the part I'm cutting. So a fair question would be, describe the shape formed by the intersection of a plane and a solid. Basically, what's the cross-sectional area? Well, when I look at this plane here, it's cutting into the corner of this cube. So it's cutting this side, and this side out. So this shape that it cuts out is a triangle. So even though I'm talking about a cube, the cross-section cut right there is a triangle. If I would take a cone and I cut this way, what I'm getting is this here. This plane is cutting straight across. I look at this oval shape. It doesn't necessarily look like a circle to me, but I'm going to say circle. Last but not least, this hexagon. It's being cut down the middle like what I showed here. The shape that's being outlined when it's cut is 1, 2, 3, 4, 5, 6-sided. So 6-sided shape is a hexagon. So these are the types of questions you'll see. You'll see questions relating to just identify the shape. You'll see questions relating to Euler's theorem. And you'll see questions related to a cross-sectional area. These are the three main sections of section 1 of chapter 12. Till next time.